Hi everyone. Now I'll be giving a demonstration on module 5, that is image restoration and reconstruction, that is noise removal. Okay, so the target is degraded digital image we'll be taking. Okay, so degraded digital image is all about the image which is very poor in giving the information to us. Okay, so sensor, digitizer, display, degradients are less considered here. Okay, so it is a combination of the module 3 and as well as module 4. Okay, so module 3 was about a spatial domain approach. Module 4 was about frequency domain approach. So here we will be using both the spatial domain and as well as frequency domain to remove the noise from the images. Okay, so we will be seeing that contents of the module 5. So module 5, first we'll be seeing a model of the image degradation and restoration process. Okay, then noise models, different types of noise models, restoration in the presence of noise only, spatial domain filtering, and then periodic noise reduction by frequency domain filtering. As I already told, it is a combination of module 3 and module 4. Then linear position invariant gradients, estimating the degradation function, inverse filtering and minimum mean square error filtering, that is Wiener filtering. Okay, so these are all the concepts we'll be learning in this module 5. So what is image restoration? Okay, so image restoration is nothing but attempting to restore the images that have been degraded. Okay, so it is almost, you can call it as image enhancement type itself only. Okay, image restoration attempts to restore the images that have been degraded, identify the degradation process and attempt to reverse it. So similar to the image enhancement, but it is more objective. Okay, so some basic example is shown here. Please see that one. Now, noise and image. So how noise will come to the image? The source of noise in digital image arise during image acquisition and transmission. Okay, so image acquisition, how we are going to do? Either by taking the photo or by scanning. Okay, so while taking the photo, if there is a dust on the lens or if there is a noise in the air, you're going to get the noise in the image. So image transmission is the process of transmitting the original image to the processed image. So while doing the transmission also, there might be chances of getting the noise. Okay, so noise model, uh, already we have learned this one. It is very simple. G of x comma y is a transformed image. F of x comma y is a original image. Neta of x comma y is a noise. Okay, so this is the noise model or equation, you can call, where f of x comma y is the original image pixel, neta of x comma y is the noise term, g of x y is the resulting noisy pixel. Okay, so pictorial representation of the previous equation will be seen. We have already seen this equation for the spatial domain. This is for the frequency domain. Okay, these two equations. Okay, so f of x comma y is a original image. We're going to degrade the function. We're going to denote it by h. Okay, so then you're going to get g of x comma y. Okay, so there you're going to add the noise to the process to restore to the original image. So the restored image you're going to call as f cap of x comma y. Okay, so the process till here is degradation and here restoration. Two process we're going to do. So different types of noise models. Source of noise, we already know, image acquisition or image transmission. Okay, so spatial properties of noise, statistical behavior of the gray level values of the pixels, then noise parameters correlation with the image. These are the spatial properties of the noise. Frequency properties of the noise is Fourier spectrum, which I have seen in the fourth module. Example, white noise. Yeah, we have seen that one. So different types of noise models also we have got. So we'll be representing the noise with neat of x comma y. Okay, so there are different types of noise model: Gaussian noise, Rayleigh noise, Erlang, exponential, uniform, and impulse noise. Okay, so all these are the different types of noises we will be adding to the image to remove the unwanted noise which are present. Okay, so this is the graphical representation of the Gaussian noise, Rayleigh noise, then Erlang, exponential, uniform, and impulse noise. Okay, so Gaussian noise is the commonly used model because the noise which will be equally distributed in between 0 and 1, that is black and white. Rayleigh also same, but it is most of the pixels will be black color, whereas Erlang and exponential always it is consists of the more black pixels. Okay, uniform and impulse noise will be on a brighter part, that is white pixels will be more in that part. Okay, we'll be seeing with the images and more examples in the coming slides. Okay, so please keep it in mind that in MATLAB, when you're implementing how to add noise, I'll be telling now. So first you need to read an image. So A is a variable here. I am read of image path. Okay. Then after reading the image, so let us consider you have taken a grayscale image like this. Okay. Then to see the histogram, what you need to do, B is equal to I am hist. What you need to use here original image, that is I am hist of A. Okay, so you have read the image first, then you have added the I am histogram, that is image histogram. Okay, so display both the images. Now I am show of A will going to display the original image, then figure comma I am show of B. Okay, so the first one will going to represent the original image. The second I am sure will going to represent the histogram. Okay, this is a simple process of creating the histogram. Now there in the previous slide we have seen different types of graphical representations of Gaussian, Rayleigh and Erlang. Okay, here you are seeing the histogram representation of the original images. Okay, so here this is the original image where we have added the Gaussian noise, and this is Rayleigh noise, and here gamma noise. Okay, so all these things will going to use when you apply in the MATLAB. Okay, so some more example of exponential, uniform, and impulse noises. Okay, so filtering to remove noise. So after adding the noise, what you need to do is, at first what you're going to do, f of x comma y plus noise, that is neta of x comma y. Okay, so you're going to add the noise. Okay, so this we can call it as f cap of x comma y for what, to remove the noise. Okay, so 1 by mn is nothing but these values, each pixel values of a mask. Okay, so this one will going to run on the image to remove the noise. Okay, we can use the spatial filters of different kinds to remove the different kinds of noises. So first example is the arithmetic mean filter is very simple one, and is calculated as f cap of x comma y 1 by n s comma t belongs to s of x comma y. This one can be called as centering the image. This one is called as centering the image. Okay, So this mask 1 by 9, 1 by 9, 1 by 9. So if the pixel value is 1 of an image, okay, when it is multiplied by 1 by 9, you're going to get some 0.1 value. So it will going to blur, or it will going to remove the values, that is noise present in that one. Okay, so other means are, there are different kind of mean filters. Okay, so one is geometric mean filter, harmonic mean filter, and contraharmonic mean filter. So this is one example. Okay, so arithmetic mean filter we have used here. Okay, so but what is happening here is, if you see this image, okay, here both salt and pepper is there. When you apply the arithmetic mean filter, so some information you're going to lose. Okay, there is more blur in this one. So you should be very choosy in using which type of filters you have to use. Okay, so it tends to lose less image detail. Okay, so some more examples. Arithmetic mean filter itself only, it will going to remove the noises such as the Gaussian noise, but other noises will be present. Okay, okay. Estimation of noise parameters. Periodic noise, first observe the frequency spectrum, then random noise with unknown PDFs, that is probability density function, which I have learned in the module 4, will be using in two cases. Case 1, imaging system is available, capture the images of a flat environment. Next is case 2, noisy images also available, take a strip from the constant area, then draw the histogram and observe it, then measure the mean and variance. Okay, so after knowing all these values, you can choose which type of filter you can apply to remove. Okay, so already we have explained this one: Gaussian, uniform. Then we'll be moving towards, after learning the noisy models, we'll be moving further, restoration in the presence of noise only, spatial filtering. Okay, so module 3 concepts we'll be using here. So degradation process we have already seen, so no need to worry about this one. So worry about the restoration filter itself only. Okay, so restoration process, what happens, g of x comma y you're going to get. Okay, so g of x comma y is what, g of x comma y is a some transformed image. Okay, so for this one you're going to add the noise like this. Okay, you're going to add the noise, then you're going to get f cap of x comma y, that is restored image you're going to get. This is about the restoration in the presence of noise only, spatial filtering. Okay, so spatial filtering have got the following filters, skills which are similar to image enhancement only, but we'll be using two more filters, that is mean filters and order statistics filters. First we will learn what are the different types of mean filters and how it will going to remove the noises in the image. Okay, so first one is mean filters, that is arithmetic mean filter and geometric mean filters, two different types of mean filters we are seeing here. F cap of x comma y, we already know why we are representing that one, because we are restoring. So f of x comma y is a original image, g of x comma y is a transformed image. For the transform image g of x comma y, so f of x comma y is a original image, g of x comma y is a transformed image. For transform image you're going to add the noise. Okay, so when you add the noise you're going to get f cap of x comma y, that is restoring image, restored image. Okay, so f of x comma y 1 by mn sigma of g of st, this is the equation used for the arithmetic mean. Okay, so geometric mean f cap of x comma y pi g of st. Okay, already I have explained that s of x comma y is a window centered. This is the examples of the image. Original image is this one. We're going to add the Gaussian noise, then arithmetic mean and geometric mean, when you apply, how actually these two images are looking after using the arithmetic mean filter and geometric mean. So after learning arithmetic mean filter and geometric mean filter, there are two more filters, that is harmonic filter and contra harmonic mean filter. Okay, so for harmonic mean filter is represented by f cap of x comma y is equal to mn, that is a pixel value, divided by 1 by g of st. Contra harmonic mean filter is represented by sigma of g of st to the power of q plus 1. So q is based on the arithmetic mean values, that is 0, -1, or +1. Okay, so it is based on what type of values you're going to take to remove the noise in the image. So pepper noise and the salt noise. So contra harmonic mean how it will going to remove the noises in both the images. Okay, so for pepper noise, contra harmonic mean works fine. Then salt noise, that is salt and pepper noise. Next, order statistic filters. Uh, so there are two types of filters in spatial filters. One is mean filters and order statistic filters. We have learned about the mean filters, different types, four different types of mean filters. That is arithmetic mean, geometric mean, harmonic mean, and contra harmonic mean. Now we will go further for the order statistic filters. So order statistic filters, four types are there. Again, one is median filter, bar min filter, midpoint filter, and alpha trimmed mean filters. Okay, so amongst all these things, median filter stands different because it will going to remove both salt and pepper noise very nicely. Okay, max filter for the pepper noise removal and min filter for the salt noise removing, it will be used. Midpoint is a combination of max and min filters. Alpha trim mean filter is to reduce the both salt and pepper noise. We will see how these filters will be used. Okay, so first is median filter, f cap of x comma y. Next, median of g of st. Okay, so I have already told that how to write a code in the MATLAB. A is equal to im read of an original image. Okay, then to add the noise for that one, b is equal to median of a comma 0.1 or 0.2 or what kind of value you want to add, that is how much noise of first you're going to add the noise, then you're going to apply median to remove the noise from the image, then you're going to show the noise free image in the display. Okay, so median filter is excellent at noise removal without the smoothing effects that can occur the other smoothing filters. Okay, particularly good when salt and pepper noise is present, as I already explained. Median filter will going to take the median of the values of the pixels, then it will going to remove both black and white noises if it is present in the image. Okay, max and min filter, it is used either to remove the black pixels or the min pixels. If you use max filter, it will going to remove the black pixels. Okay, so salt and pepper is a noise, okay, where salt is a white color pixel noise will be there, and pepper is black color pixel. Okay, so max filter is very good to remove the black color noise present in the image, and min filter is very good to remove the white color pixels noises present in the image. Okay, max filter equation is given by f cap of x comma y is equal to max of g of st, and min filter equation is given by f cap of g of x comma y min of g of st. Okay, max filter, I already told this one, max filter is good for pepper noise and min filter is good for salt noise. Okay, this is one example. So median filter, this is bipolar noise is nothing but you're going to say both. Bipolar is nothing but both noise and, sorry, so salt and pepper. Okay, so 3 cross 3 median filter, how it is removing the noise in three different run. Okay, at first run this is the output, second run this is the output, third one still more purified image you can see. Okay, so for pepper noise, that is black noises, max filter is best. Salt noise, for white noises, min filter is best. Okay, so pepper noise, black pixels you're seeing more in this image. Salt noise, white pixels you're seeing more in this image. So when you add the pepper noise or the salt noise, you can use max filter or the min filter respectively. Okay, so order statistics filters continuing. We have seen median filter, min and max filter. Now midpoint filter is a combination of min and max. So it is represented by half of max g of st plus min of g of st. Okay, alpha trimmed mean filter is nothing but 1 by mn minus d. D is the total number of middle pixels. Mn minus d is the total number of pixels present in the image, that is middle pixels present in the image. G of st itself only. Okay, so midpoint filter, we have seen it is good for random Gaussian and uniform noise to remove. Next, alpha trimmed is used to highest gray levels image. When you're going to use, there you're going to delete both black and or reduce both black and white pixels. It doesn't remove perfectly, but it will going to reduce. Okay, so uniform noise, then arithmetic mean filter, median filter, then alpha trim filter, geometric mean, and bipolar noise. Okay, so the results are given here. Now we have seen in the spatial filtering domain, that is module 3 concepts are over now. Next, periodic noise reduction by frequency domain filtering. Okay, so periodic noise reduction is a combination of impulse noises. Okay, so something like if noise is present in the image, we can consider as a pair of noises. Is if salt is present, pepper also will be present. Okay, that is one simple example. Okay, so pure sine wave will be taking appear as a pair of impulse, that is impulse noise I have already told in the frequency domain. F of x comma y is equal to a sine of u x and vy. Okay, this equation we have seen in the module 4. Further, in the frequency domain, if you want to see, f of u comma v can be written as minus j of a by 2, delta of u minus u by 2 pi, v minus v by 2 pi, minus delta of u plus u by 2 pi, v plus v by 2 pi. If you apply this equation, you can remove the noise in the image. Okay, so here it is a representation. Already we have seen in the spatial domain, degradation was removed there, only we have given concentration on the restoration of the filter. But here again coming back, so f of x comma y, already you know what is degradation function, that is degrading the image. You'll go into the degraded image can be represented as g of x comma y. You'll go into add the noise for g of x comma y. You'll go into get f cap of x comma y, that is restored image. So estimating the degradation function in three ways: estimation by image observation, next is estimation by experimentation, estimation by modeling. So image observation, you're going to estimate how many on how much of black pixels or white pixels is present by looking at the spectrum. Then experimentation is nothing but checking at a different levels, pass 1, pass 2, pass 3, etc. You're going to run the filters again and again over the image to remove the noises. Then you're going to have combinations, which filter is suitable for which kind of noise. Then estimation by modeling. Modeling is nothing but you're going to calculate the total number of pixels that already equations we have seen. So g of x comma y plus net of x comma y into f of x comma y is the model. to estimate the total number of unwanted pixels present in the image. Okay, fine. Estimation of image by observation, the first point. Okay, take a window in the image, simple structure, strong signal content, estimate the original image in the window. Okay, so to estimate, you will be having known and as well as estimate. So it will be represented as for image observation, h of u comma v is equal to g of u comma v divided by f of u comma v. So here keep it in mind, already we know this one. Again and again I'm repeating this one. So this equation, don't forget, g of x comma y is equal to t of f of x comma y. Okay, so this f of x comma y can be represented as f of u comma v. Okay, so when you add the noise to g of x comma y, you will going to get f cap of x comma y. This f cap of x comma y can be represented as f cap of u comma v also. G of u comma v is this one. So this is already known because we have calculated by applying some transformation. So degradation has already happened. So for that one, you'll go into calculate the total number of noise pixels added to that one. Then only you can observe the image properly. That is represented as hs of u comma v. Okay, so estimation of by modeling, already experimentation have shown in the previous slides that how noises are added to the images, and how many types of filters you're going to use, and how many levels you're going to run to remove the noises. Now estimation by modeling. Okay, this is one model, h of u comma v. For modeling, you can call it as e to the power of minus k, that is constant value, u square plus v square to the power of any value, 1 2 3 5, as any value you can keep. So this is the original image, this is the degraded image. At lower the value, lower you're going to get, higher the information you're going to get. Okay, so mathematical model can be represented as g of x comma y is equal to integration of 0 to t or infinity f of x minus x naught of t y minus y naught of t. So this is a Fourier transformation if you want. These are the planar motion. In Fourier transformation, if you want to mention, g of u comma v is equal to f of u comma v. F of u comma v is the original image. This is a transformed integration of 0 to t, some constant values. Okay, so next one will be estimation by moving, that is motion model. So what if the image is in motion, that is while taking the picture, if the image is moved from one position to another position, you can create by applying the motion model also. Okay, so the next comes the inverse filtering. So inverse filtering is nothing but to remove back the estimated degradation functions of h of u comma v. So h of u comma v is the degradation function. G of u comma v is equal to f of u comma v into h of u comma v plus noise. Okay, so to estimate the original image, you're going to calculate f of u comma v is equal to g of u comma v by h of u comma v, can be written as f of u comma v plus noise, this is unknown noise, then h of u comma v is a degraded problem. Okay, so this is nothing but one image where degraded example. Next comes the minimum mean square error filtering or Wiener filtering. The Wiener filtering can be used to filter out the noise from the corrected image to provide an estimate of underlying signal or image noise or noise of interest. Okay, so it is basically a statistical approach, and Wiener filtering is very optimal for the minimum mean squares. That is why we are using the Wiener filter for the minimum mean square error filtering, and it minimizes overall the mean square errors in processing of the inverse filtering and noise smoothing. So minimum mean square or least square filtering can be represented as h of u comma v, w1 comma w2 here. one more representation you are seeing. Okay, so w1 comma w2 is nothing but u comma v or x comma y. You can represent it in your own way. Okay, h of u comma v divided by modulus of h of u comma v whole square plus k. So k is a constant value you are going to add. So k is a combination of noise energy and as well as a signal energy, which is used for inverse filtering. Okay, goal: have an inverse filter that deals with the noise better than the inverse filtering. Try to minimize the value, that is more number of noise present in the image. Okay, so we'll be using the power spectrum for that. The power spectrum is represented by what? H of u comma v, modulus of h of u comma v whole square. Okay, so that is all about the module 5. Thank you so much.